Hi, I'm Mohammadreza Behrouzi. We are proud of ourselves that you watch our videos and we can make a small contribution towards your knowledge improvements. These videos that we have uploaded on our website or on our YouTube channel consist of notes and real case examples from our last projects. Those projects were performed by a team of professionals and experts. Therefore, by watching these videos, you can gain tremendous amount of knowledge and experience by which you can design your process units, your plants with highest safety. You are our only sponsor. So if you enjoyed the video, at the end hit the like and subscribe so that you can get informed about our latest videos. This video is allocated to biocides. But before going to elaborate on biocides, I want to give you an introduction about oxidizing and non-oxidizing biocides, what oxidizing and non-oxidizing biocides are, and their differences and the most important types of each category. Here we have oxidizing and non-oxidizing biocides. Microbiocides fall into two broad groups: oxidizing biocides. Oxidizing biocides kill bacteria by destroying cells. Membranes are blocked so that the cells cannot metabolize. The more powerful oxidants actually break down cell walls. Some less powerful oxidants can penetrate cell walls and oxidize internal cell structure. Chlorine and sodium hypochlorite bleach solutions are by far the most widely used oxidizing biocides, followed by bromine compounds and other oxidants. Oxidizing biocides can be applied as a continuous low-level dosage or as intermittent slug doses. Best results are usually obtained with low-level continuous dosage of 0.1 to 0.3 ppm, plus, if needed, occasional higher slugs up to 1 to 2 ppm for cleaning. Because of the reactivity of oxidizing biocides, residuals do not last long, so that to maintain a residual dosage, continuous feed is needed. Non-oxidizing biocides do not destroy cells. Rather, they are absorbed through cell membranes into the cell, where they interfere with metabolic processes, mostly enzyme productions. For this reason, non-oxidizing biocides are sometimes called metabolic biocides. A wide variety of organic compounds are used as microbiocides, including quaternions, sulfur compounds, aldehydes, nitrogen-ring compounds, and others. Non-oxidizing biocides are more expensive than oxidizing biocides and larger dosages are required. However, because reactivity is lower, high dosage can be used to provide a residual that will often last for days. So, to summarize what we have learned from this text, we have two types of biocides: oxidizing biocides and non-oxidizing biocides. Oxidizing biocides kill bacteria by destroying cells, while non-oxidizing biocides do not destroy cells. They are absorbed through cell membranes into the cell, where they interfere with metabolic processes and mostly enzyme productions. So they interfere with metabolic processes, while oxidizing biocides destroy cells of bacteria. The most important, the most powerful oxidizing biocides are chlorine and sodium hypochlorite, while the most common compounds of non-oxidizing biocides are quaternions, sulfur compounds, and nitrogen ring compounds. Oxidizing biocides can be fed to the uh, cooling water systems in a continuous dosage or in an intermittent manner. In a continuous dosage, zero point 0.1 to zero point 0.3 ppm of this is required in order to have the cooling water system clean. And of course, occasional higher and for non-oxidizing biocides, these are uh, in fact fed. These are injected to the cooling water systems in a shockwise manner. And the last one, non-oxidizing biocides are more expensive than oxidizing biocides, and larger dosage of them are required. But remember, they will last longer. They will last for days. Table 4 and table 9 and table 10 contain lists of oxidizing and non-oxidizing biocides that are commonly used in cooling water systems. All of these biocides and other are discussed in more detail later in this section. For common oxidizing biocides, we have chlorine, chlorine dioxides, bromine, and ozone. And their performance against different types of, as you can see here, their performance against bacteria, fungi, and algae are evaluated and compared. E stands for excellence, G stands for good, and S stands for slight active against those slight activity against those bacteria, fungi, or algae. Here, as you can see, their activity against bacteria for all of these chlorine dioxides, bromine, and ozones are excellent. Only chlorine dioxides and ozones have good performance, have good activity against fungi and algae, as you can see here. But bromine and chlorine, their actions, their activity against those fungi and algae are slight. And let's see more details about chlorines and other microbiocides here. Chlorine reacts with these groups effective at neutral pH about 7, for instance 7.5, 7.4 has the best excellence, has the best performance, may be less effective at high pH. Use concentration of zero point 0.1 to zero point 0.2 ppm free residual continuous free residual and zero point 0.5 to 1 ppm intermittent free residuals. These kind of recommendations are in fact good to be followed, but I have one experience I want to talk about it. I've been using coloring products, especially uh, calcium hypochlorite, for about 3 years for the cooling water of this for the cooling water system of the company I work for. And of course, I've reached this conclusion that if the coloring compounds are injected on a daily basis and the performances of them and their injection, their consumption, their feed rates are in fact monitored daily and in a good manner, in a meticulous way. There is no need to have such high, no need to maintain the free residual of coloring into such limitations. Sometimes it is, for instance, 0.05, sometimes it is 0.02, and sometimes it is trace, even though you know that it is fed continuously. And of course, for instance, I've seen that for more than 1 week, all of these chemicals residuals were traced, but we didn't observe any kind of fungi or bacteria on the walls of the cooling water systems. And of course, I like this recommendation. It is a good recommendation. It should be followed because most time we follow these recommendations and we try to maintain the residual between zero point 0.1 to zero point 0.2 ppm of the color. But if but what I'm saying that if sometimes this you can get such free residuals even though you are injecting chlorine compounds on a daily basis, it don't worry about these ones because it sometimes happens. But I want to make you sure, I want to ensure you that they, in fact, are fighting against this bacteria. They have good performance, and you're not going to see any kind of, algae or bacteria on the wall of your cooling water systems. It is a good recommendations, but if for 1 week, 2 week you are not able to be able to see the free residual within the to maintain the free residual within this limitation, don't worry about this ones. Chlorine dioxides, pH insensitive, can be used in presence of these groups. Use concentration 0.1 to 1 ppm intermittent free residual. Bromine, substitute for uh, color, effective over broad pH range. Use concentration 0.05 to 0.1 ppm continuous free residual and 0.2 to 0.4 ppm intermittent free residuals. Ozons, effective over broad pH range, continuous or intermittent feed of 0.2 to 0.5 ppm. Then we have this table. This table represents the most common types of non-oxidizing biocides. Here, of course, I'm just going to talk about the most four of the most common type: isothiazolene, quartariammonium, and glutaraldehyde, organic thine quartariammonium salts, of course five of them, and organic bromine compounds. I'm going to start with isothiazolene. It has excellent activity against bacteria and good performance against fungi and algae. It is pH sensitive, deactivated by Hs and uh, NH2 groups. Use concentration 0.9 to 13 ppm intermittent feed. As you can see, as I stated, non-oxidizing biocides are fed intermittently on, for instance, week basis, on a weekly or 2 week basis. Then we have quartariammonium salts. Excellent performance against bacteria and good performance against fungi and algae. Tendency to foam, surface active, ineffective in highly oil or organic fault system. Use concentration 8 to 35 ppm intermittent feed. Then we have glutaraldehyde deactivated by NH2 groups, effective over broad pH range. Use concentration 10 to 75 ppm intermittent feed. We have organic bromine compounds, pH range 6 to 8.5, use concentration 0.5 to 24 ppm intermittent feed. Of course, there are other types of uh, non-oxidizing biocides, but they are not used as commonly as the biocide I talked about. Then here we have biocide demand. One important reason for regular tower cleaning is to maximize the effectiveness of biocides. Oxidizing biocide will react with many other materials in the cooling tower besides bacteria. Other organic chemicals, oxidizable inorganic chemicals such as ferrous iron, other reactive chemicals such as amines, suspended dirt, and clay, etc., all will react with oxidizing biocides. So, some oxidizing biocides such as calcium hypochlorite react with anything that is in their ways. It can be dirt, it can be clay, it can be bacteria, it can be amines. They react with anything that they find in their ways. Non-oxidizing biocides also react with substances other than bacteria. These are mostly polar organic molecules that have an affinity for surfaces. They absorb readily on suspended solids so that the amount available for free circulations in the water is reduced. These concepts can be quantified in terms of demand. The demand for any biocides in a specific system is the amount in ppm that must be added to the system water before a measurable free residual can be maintained in the systems. With oxidizing biocides, the demand is easily measured by laboratory titration to the first appearance of a stable free residuals. In field situations, where a quick demand number is needed to estimate required dosage, for example, DBD test, can be used for rough demand estimates. Measuring the demand for non-oxidizing biocides is harder because analytical methods are not available for all biocides. Non-oxidizing biocides are usually dosed based on system volume, and if possible, the measured residual is compared with calculated volumes. If tests are available, analytical measurements of biocide residual versus time are a good way to detect the presence of biofilms or other microbiological deposits in systems. So, so far, we have talked about what oxidizing biocides are and what non-oxidizing biocides are. We have talked about the mechanism of killing bacteria for oxidizing biocide and non-oxidizing biocides. And of course, we have talked about different types of oxidizing biocides, their performance against different, bacteria, fungi, algae, and the situation that they are, the environment in which they are most effective, and of course, the required dosage of them in order to be effective against these bacteria and fungi and algae. Then we talked about uh, four of the most commonly used of non-oxidizing biocides. Most commonly used non-oxidizing biocides, four of them: isothiazoline, quaternary ammonium salts, and DBNPA, and of course glutaralate, and talk about the environment in which they are active against this kind of bacteria, fungi, and algae. And of course, we said that non-oxidizing biocides are injected intermittently, while oxidizing biocides are mostly injected in a continuous dosage with a continuous dosage. In these episodes, from now on, I want to elaborate on non-oxidizing biocides. By the way, you can go to my websites and download or watch uh, the episodes about oxidizing biocides. In that episodes, I have explained excessively about the characteristics of different types of oxidizing biocides. For now, let's focus on non-oxidizing biocides. Here, as I explained earlier, these four biocides are the most uh, commonly used biocides, non-oxidizing biocides that are used for cooling water systems in oil and gas industry. We have isothiazoline, glutaraldehyde, and DBNPA. Of course, its name is too long that I want to use the abbreviation for. Then we have quats or quaternary ammonium compounds. Of course, here is the brief and concise explanation of mechanism, advantages, and disadvantages of each of these non-oxidizing biocides, but later we will explain excessively about each of these biocides. I'm going to start with isothiazoline. Isothiazoline penetrates cell membrane to deactivate enzymes needed for cell to survive. Its advantage over other non-oxidizing biocides is that it is effective on both bacteria and fungi, persistent in system synergism with oxidizers, actively activity over wide pH range. Its disadvantage: inactivated by sulfide contamination. Concentrated isothiazoline is a skin sensitizer. So based on this, and of course, I've used isothiazoline for more than 3 years for my cooling water systems. And of course, whenever I want to use it, I use it with oxidizers such as calcium hypochlorite. Why? Because it has a great synergism with oxidizers. And of course, its activity over a wide pH range, and it is extremely persistent in system. I have experienced this persistency firsthand. After one day, still there are some. After 2 days, still there are some dosages of residuals of isothiazolines in the cooling water systems. Then we have glutaraldehyde. Glutaraldehyde, its mechanism is in this way: cross-linking of two adjacent amino groups in cell wall proteins impairs cell functions. Advantages: very effective in normal pH range of cooling water systems. And its disadvantage: reacts with halogens, ammonia, organic amines but not quaternary amines, should not be applied in the system with these contaminants or with oxidizing biocides. So if you use oxidizing biocides such as calcium hypochlorite, it is better not to use glutaraldehyde as the non-oxidizing biocides for your systems. Another things, if you have tested that there are some residuals of ammonia in your cooling water then it is better to not use glutaraldehydes. For instance, one of the reasons that I had this experience, not firsthand, but one of nearby petrochemical cooling water systems were using glutaraldehyde, and of course, unfortunately, after 2 months or 3 months use of glutaraldehyde, their cooling system was this biocide was not effective in that manner to remove bacteria and to eliminate fungi. And of course, we were talking about these matters, and of course we were checking a lot of operating manual, which are checking a lot of water treatment handbooks, and we came across this sentence that if there are some traces of ammonia, if there are some traces of halogens in your system, it might not be active against the bacteria. And of course we did some tests and found out that there are some high amount of ammonia in their systems, and because of the presence of those ammonia, it was glutaraldehyde was not a good choice of non-oxidizing biocides for that cooling water system. And after 1 week, we changed. In fact, they changed the these non-oxidizing biocides for their systems, and after 2 months of use of, in fact, they changed it to isothiazolene, and after 2 months of 2 months use of isothiazolines, the activity of isothiazoline against that bacteria were laudable, were really amazing, and there was no fungi, or let's say those green substances on the wall of the cooling water systems, and everything was clean and neat. Then we have DBNPA. It reacts with cellular membranes and enzymes, causing disruption of cell metabolisms. Advantages: it is fast against bacteria, and disadvantage: lack of persistence, rapid hydrolysis at high pH, high cost relative to other biocides, less effective for algae and fungi. Then we have quartz. They binds or anionic components of cells and cell walls. Their advantage is that its advantage is that it is generally effective against bacteria, fungi, algae, and have surface active dispersing properties. When you use quartz, of course, for some period of time, I used quartz as one of the biocides for my system, as one of the non-oxidizing biocides for my system for about 3 months. And of course, when I was using these quartz, there were some foams were created when I was injecting in fact, the quartz in the cooling water. So when you use quartz, the consumption of biodispersants reduces. As you know, biodispersants are those substances, those chemicals which are added to cooling water systems in order to disperse some conglomerations and and inhibits scales from sitting on the surface of a cooling water system. And when you use quartz, since it has some surface acting properties, the demand for biodispersion reduces, and it is a good thing. And because biodispersants uh, create some foams when they are added to the systems, and because of those foams, they reduce the tension between surface and those scales. And since it has surface actives, it can help biodispersants. And of course, its disadvantage is that it can cause foaming and can inactivate anionic polymer dispersants. If it is formulated with high foaming, it can be a problem. But in a normal way, it is not that much problem. So now I want to focus on each of these. Here, I just talk about the general aspects of each of these non-oxidizing biocides, about their mechanism, advantages, and disadvantages. But I haven't talked about their groups. I haven't talked about the way they are formulated and the way they are supplied to the market, and the supplier of those non-oxidizing biocides in the world, in the international market, and a lot more. I'm gonna start with isothiazolene. Isothiazolene is alkyl isothiazolene 3-1 organosulfur group, good wide-spectrum bactericides and algaericide that is effective over a wide range of pH. Isothiazolines kill by inhibiting microbial respiration and food transport through the cell wall. It is recognized as an industry standard product for cooling systems but can be expensive. Isothiazolines are supplied to some markets as a 13.9% active concentrated blend. With this formulation, here we have about, of course, these formulations consist of two products, two components here. This component, about approximately 10% of this component, and about 4% of these components by 40% active concentrated blade, but it is always marketed to the end user as a 1.5% active, uh, about 1.11% of this component, and 0.4% of this component, or or 1.15% of this component, and 0.35% of this component. Let me show you two products of two manufacturers of this uh, isothiazolines. I want to show you that around the globe this formulation is constant, and of course there is no change in isothiazoline formulations, and I mean from manufacturer to manufacturer this formulation doesn't change. They all use these components and these components, but the percentage might change a little. For instance, for this manufacturer, as you can see, 5-chloro-2-methyl-4-isothiazoline 3,1 plus 2-methyl-4-isothiazoline 3,1. The same happens for this one, 5-chloro-2-methyl-4-isothiazoline 3,1 and 2-methyl-2-H-isothiazoline 3,1. As you can see, 5-chloro-2-methyl-4-isothiazoline 3,1s and 2-methyl-4-isothiazoline 3,1s. The same uh, for all of these manufacturers, for this manufacturer, and for this catalog. As I said, it is supplied to the market by 40%, 14% active concentrated blend, but to the end user it is 1.5% active. Isothiazolines are amber to yellow-green liquids that require very careful handling due to the severe skin and eye irritant properties. They are effective against both general aerobic and spore-forming bacteria over a pH range of 6.5 to 9. Isothiazolines are very effective algicides and fungicides, but only add acid to a slightly alkaline pH levels. Contact time is typically 5 to 6 hours. Dose rate is typically 50 to 120 ppm for 1.5 active isotiazolines. Availability exists as several possible permutations of the product under these companies. These companies, as you can see, these are the companies which are highlighted here, provide the in fact isotiazoline to the market. You can see here, you can download the in fact the this PDF from my websites and check with these companies the isotiazoline product. So before going to the next non-oxidizing biocides, I want to wrap it up. I want to summarize it and do a calculation about the yearly, about the monthly, consumption of isotiazolines. So it is uh, alkyl isotiazoline 3,1 organosulfur group, and it is active against allergy and bacteria. It is supplied to the market by 14% active concentrated blend by to the with these formulations 5-chloro-2-methyl 4-isotiazoline 3,1 plus 2-methyl 4-isotiazoline 3,1. But uh, to the end user, it is 1.5% active. This was for supply to the market. This way, the supply to the end user, and of course with these formulations, with the exact formulations, but their concentration is against is like this one or like this one. And of course they are effective against both general aerobic and spore forming bacteria over a pH range of 6.5 to 9, and their contact time is typically 5 to 6 hours. Dose rate is typically 15 to 50 to 120 ppm for 1.5% active isotiazolines, and these are the companies which produces isotiazolines. So in order to calculate the uh, required dosage per each injections, I want to allude to one of the important paragraphs I mentioned at the start of our lecture about the biocide demand. Here it says non-oxidizing biocides are usually dosed based on system volume. It's an important sentence and all calculations are based on this sentence. So if I want to calculate the required amount of non-oxidizing biocides, I have to base my calculations on system volume. But how I'm gonna I'm gonna calculate the consumptions of isotiazoline per each injection to make you better understand how to calculate uh, non-oxidizing biocides demand for your applications. Here is the typical example. For my system, the system volume is 7,500 cubic meter. For your system, it might be 5,000. You should check the documents of your system and sum up the volume for the basin of your cooling water system plus the whole cooling water which is in the piping, the volume of those piping which contains cooling water plus the volume of basin. For my system, it is approximately 7,500 cubic meters. We know that the required dosage of isothiazoline in the system is 50 ppm. Why? Because here it says that for it says here dose rate is typically 50 to 120 ppm for 1.5% active isothiazoline. If I want to the isothiazoline to be active against bacteria, it should be at least 50 ppm. So I consider it to be 50 ppm, and required dosage per each injection is calculated in this way. At first, I know that I need this ppm. So I multiply this ppm by the volume of the systems and do some conversion here between the liter and cubic meter and between kilogram and milligram. If I can cancel this one with this one, and I can cancel this liter per liter and cancel this milligram by this milligram, at the end I will have the kilogram. If I do this simple calculation, I get this amount, approximately 400 kilogram per each injections. Each injection is done based on 2 week is done based on 2 week. For one company, it might be on weekly basis. I myself, for I prefer to inject the non-oxidizing biocides such as isothiazoline on 2 week basis. So you should check which one is suitable for your applications. Sometimes your cooling water system demands that the non-oxidizing biocides should be injected weekly, but sometimes it demands that cool non-oxidizing biocides should be injected on 2 week basis. For my systems, if I inject the non-oxidizing biocides on 2 week basis, it is enough. Everything is clean, and everything is on the safe side. So in the 1 month, I need 2 injections, and in each injection, I need approximately 400 kilogram. Per month, I need 800 kilogram. And since every gallon contains 200 kilograms, for each month I need 4 gallons of isothiazoline to be purchased and be brought to the site. Then we have next non-oxidizing biocide, glutaraldate, pentane 1,5-diol aldate group. Glutaraldate is a good bactericide, especially with difficult and persistent organisms due to its good penetrating ability. It has limited effectiveness against algae and fungi. The kill mechanism is by cross-linking outer proteins of cell and preventing cell permeability. Hi, I'm Mohammadreza Behrouzi, the manager of Educational Institute for Equipment and Process Design. I hope that you have enjoyed every moment of this video. I highly recommend you watching videos instructing heat exchanger designs from our websites or through our YouTube channel. By watching these videos, you become not only familiar but also professional in thermal and mechanical design of shell and tube heat exchangers. So far, if you have enjoyed the video, hit the like and subscribe. Glutaraldate is a fast-acting biocide, 3 to 4 hours, perhaps 4 to 6 hours, with difficult steams, non-ionic, non-foaming, effective over a wide pH range, typically pH 6.5 to 9. It is also effective against SRBs and biofilms. The half-life tends to be short, depending upon the particular cooling system's parameters, but typically 4 to 12 hours. Careful evaluation is needed before application on some larger systems, especially as it may not be particularly cost-effective. Glutaralate is readily biodegradable. Typical use concentration is 100 to 125 ppm at 40% at 45% active material. Also, heavily steam cooling system may need 200 to 300 ppm as an initial cleanup shock dose. It is an effective choice for biological control in an air washers. Glutaralate is probably a good biocide where the risk of this exists. Although concentrated glutaralate reacts with ammonia at typical in use concentration, the rate of reaction is slowed, and glutaralate can be suitable for SRB and steam removal in large process systems, where 25 to 15 ppm or more of ammonia is present. This biocide is particularly associated with this company, a subsidiary of the Dove Chemical Company. So here was the all information about glutaraldehyde. We know that to the end user it is supplied by 45% active materials. The dosage for end user should be 100 to 125 ppm in a typical cooling water systems. It's fast acting biocides, and killing hours is 4 to 6 hours. Its half time about 4 to 12 hours, and its mechanism is based on cross-linking outer proteins of cells and preventing cell permeability. Of course, for cooling water systems, heavily steam cooling water systems, more dosage of this might be required to 200 to 300 ppm of this. Now, let's have a discussion on the consumption of the glutaralate for cooling water systems. For my system, for instance, system volume, as I said, is 7,005 cubic meters. Uh, the required dosage is 100. Here I've brought the 100 here. It is misspelled, misprinted. Sorry for that. And here I've written down 100 ppm of that one. The required dosage per each injection is this one, is multiplied by the volume of the systems, and here you can see the conversion between liter and cubic meter and the conversion between kilogram and milligram. And finally you need approximately 800 kilogram per each injections. And since my injection is on 2 week basis, I need 1600 kilogram, and each gallon contains 200 kilogram. It means that I need 8 gallon per month for in fact for glutaraldehyde to be purchased and be brought to site. But remember, for isothiazoline I needed 4 gallon. Here I need 8 gallon per month. Then we have quartz. Uh, Quartz, you can see the long name of this one, and of course shortly some experts say that it is it is called benzalkonium chlorides. Quaternary ammonium compound groups. There are many popular products in this group that are widely available. The primary amine salts are of limited benefits in cooling water in cooling systems, but diamine quartz are effective. Quartz are cationic surface-active products with a tendency to form, as I stated earlier, especially above pH 8. The kill mechanism is due to the cationic nature, whereby an electrostatic bond is formed with the cell wall, which affects the permeability and protein denaturing. Quartz are effective algaecide and reasonably good bactericide and can be applied over a wide range of pH. Optimum pH 6.5 to 8.5. At typical in-use concentrations, diamines will help maintain clean cooling systems and reduce population of general algal and bacterial organisms. However, they tend to have only a bacteriostatic effect over this type of bacteria and ascorbics. An advantage of quartz is their relatively low cost. The disadvantage is that quartz are deactivated by high hardness, typically over 500 ppm, colorides, oil, dirt, silt, and debris. Quartz have poor compatibility with polyanionic polymers. Typical end-user product is 10% active strength quartz in an alkene solution with a dose rate of 50 to 100 ppm. Contact time is typically 4 to 6 hours. Uh, Examples of quartz concentrators are these products. You can check these products on the internet, and if you need, you can contact. So, to wrap it up, to summarize this, quartz are benzyl conium chlorides. The most effective type of quartz are diamine quartz. They are effective. They can act against bacteria with the optimum pH of 6.7, 6.5 to 8.5. And of course, their advantage is that they are low cost, but their disadvantage is that they are deactivated by high hardness chlorides, oil, dirt, silt, and debris. That's one of the bad things that happens to quartz. And you might increase the quantities of the quartz which should be injected to cooling water systems in order to overcome these problems. And their contact time is 4 to 6 hours. They are supplied to the end user, not to the market. They are supplied to the end user with 10% active strength quartz, and the dose rate of 50 to 100 ppm of them are required is required. Yeah, for about 3 months, I used quad as non-oxidizing biocides for my cooling water systems, and I have some first-hand experience with this quad. And as I stated, when I first injected the quad into my system, I saw some foaming, and as you can see here, a tendency to foam. I saw those foamings, and of course, I had some consultancy with the manufacturers, and they said they gave me this catalog, and they said that they are in fact surface active property. They have some surface active properties, therefore they can help you in the with help you with the reduction in the consumption of biodispersants. And of course, we did so. We reduced, since they were surface active and since they were producing some foams, it meant to us that they were helping biodispersants. So as a result, we reduced the consumption of the injection of biodispersants, and it was good experience. But the problem with quads that I experienced it, I encountered this by my hand and first hand, was their inactivations. Here, they are deactivated by dirt, silt, and debris. When I were, for instance, when I on first day when I was injecting them with high concentrations, here it says, for instance, it should be between this value, between 15 to 100 ppm. And for instance, on first day it was about 45 ppm, approximately 50 ppm. But the next day it was 20 ppm. The third day it was, for instance, 1 ppm. For other occasions, the first shock residual was, for instance, 3.5 ppm, and the next day was trace. We were, really baffled. It was a kind of puzzling to us to why it happens in this way. Then we saw this, catalog, saw this, in fact, these informations, and concluded that since there were some dirts or debris or other of that types, it might deactivate the chloride, it might deactivate the quartz, and the performance and impact their performances against bacteria. Therefore, we had to change the quartz to isothiazolene. And for its consumption, system volume is this value, and required dosage, the minimum required dosage is here 15, and of course required dosage per each injection is like isothiazolene. 15 is multiplied by the volume system, and the conversion between liter and cubic meter and kilogram per by milligram. If you multiply this, you get this value. It means that and it means that per each injection you need about 400 kilogram. Since in 1 month 2 injection happens, you need 800 kilogram, which means that you need to purchase 4 gallon of quad per month for your system. The last one is DTA. It is from this group. This is one of the few genuinely new biocides to enter the market in recent years. DTA was designed to operate effectively under a wide range of pH level, pH 6 to 10 or greater, but especially for the higher pH now common with all organic or similar high alkalinity tolerant inhibitor programs. It was also designed as a specific sessile bactericide, biofilm remover, and biofilm growth control agents. DTA2 functions by forming reversible chellant complexes with the salts and inorganic ions found in biofilm structures, which severely weakens the biofilm and reduces its adhesiveness. DTA are highly surface active and can be thought of as a biocidal soap to be used for cleanup programs. As a biocide component with chlorine, although it is not recommended to be used at the same time as chlorine, and as a maintenance biostat, application rates are typically 50 to 100 mg per liter. It is consumed and decays rapidly in heavily fouled systems, typically in 3 to 4 hours. Consequently, it is recommended to slowly add the complete dose over a 4-hour period. Consequently, it is recommended to slowly add the complete dose over a 4-hour period. DTA or DTA is manufactured as a 15% active material. It is distributed primarily through AMSA corporations in the USA. So let's wrap it up and calculate its consumptions. It is distributed and manufactured with 15% active materials. The typical rate is between 50 to 100 ppm. In heavily fouled systems, it is consumed in 3 to 4 hours, and the mechanism of this is by forming reversible chellant complexes with the salts in biofilm structures. And of course it can operate It can be used under a wide range of pH levels from 6 to 10 or greater. And its consumption, the system volume is this value, and of course the minimum rate should be 15. Therefore, the same happens here, and 400 kilogram per injection is needed. Therefore, in months, we need 800 kilogram of these non-oxidizing biocides, which means that we need you need to purchase 4 gallon of this non-oxidizing biocide and be brought to the site to be used for cooling water systems. So let's review what we have learned from the start of the lecture to the end point. At first, we talked about oxidizing and non-oxidizing biocides. We talked about their mechanism. Then here we talked about common oxidizing biocides, their characteristics, and their performances against bacteria, fungi, and algae. Here we talked about some of the most usually non-oxidizing biocides here. Then we talked about biocide demands. Here we stated that if you want to calculate the consumption of biocides, the calculation should be based on system volume. Then here we talked about 4 important non-oxidizing biocides, talked about their mechanism, their advantages, their disadvantages. And at the end, we focused on each of these non-oxidizing biocides characteristics, formulations, the way they are supplied to the market, the way they are supplied to the end users, their performances over a pH range, and the company and manufacturers that produce these products. And for each of these non-oxidizing biocides, we calculated the consumption per each injection and per month. We did the same for glutaralate, for isothiazoline, for quartz, and of course DTEA. I hope that you have enjoyed every moment of these episodes, and you will be able to use this knowledge, use these procedures and informations in order to select the best type of non-oxidizing biocide for your application. Uh, I wish you good days and enjoy your life.